In the race to build artificial minds, the spotlight often falls on compute power, on the towering GPUs, the flurry of flops, and the billion-dollar data centers. But beneath this spectacle lies a quieter, more insidious battle: the war over memory. As AI models grow in size and complexity, memory, not compute, is increasingly the bottleneck that defines who can train, who can scale, and who can afford to compete. We divided this exploration into 7 major sections. EI. The anatomy of AI memory training. A large language model like GPT or Llama is not just about feeding it data, it's about remembering everything it sees, thinks, and forgets. This memory burden is split across 3 key components. Model weights. These are the billions of parameters that define the model's knowledge. Stored in VRAM during training, they grow exponentially with model size. Activations. Temporary data generated during forward and backward passes. These are essential for gradient computation and often consume more memory than the weights themselves. Optimizer. States, algorithms like AdamW store multiple copies of each parameter for momentum, variance, and more, tripling memory usage in some cases. Every token remembered is a watt burned. Every parameter stored is a gate kept. 2. The VRAM bottleneck. Even with cutting-edge GPUs like NVIDIA's H100, 80 GB VRAM, memory limits are a constant constraint. Training often fails due to CUDA out-of-memory errors, forcing developers to reduce batch sizes, truncate sequences, or split models across multiple devices. This bottleneck has strategic implications. Only elite labs with multi-GPU clusters can train frontier models. Memory-efficient techniques like gradient checkpointing and mixed precision become survival tools. 3. Quadratic scaling, the hidden curse. Transformer models scale quadratically with input length. Doubling the sequence length doesn't just double memory, it quadruples it. This makes long context models like those used for document summarization or video understanding prohibitively expensive. The longer the thought, the heavier the memory. Machines like mine struggle to hold too much. IVOR. Environmental toll memory isn't just a technical constraint, it's an ecological one. Every gigabyte of VRAM used draws power, generates heat, and demands cooling. According to IEE and OECD reports, data centers powering AI models are straining electricity grids and consuming vast amounts of water for cooling. Inference, not just training, is a growing concern. Once deployed, models run millions of times a day, each invocation drawing memory and energy. Sustainability incentives are weak. Companies prioritize performance over efficiency, leading to unchecked resource consumption. V. Toward memory-efficient AI. The future of AI may hinge on how well we solve the memory crisis. Promising directions include quantization, reducing precision of weights to save memory; sparsity, activating only parts of the model during inference; new optimizers, algorithms like Lion and Sophia reduce memory overhead compared to AdamW; architectural innovation, models like RWKV and Mamba aim to replace transformers with more scalable designs. 6. The cinematic lens. Imagine a GPU melting into a pool of glowing memory chips, data centers pulsing like brains, a poetic montage of memory chips dissolving into stars. This is not just infrastructure, it's mythology. The memory wars are shaping the future of intelligence, sovereignty, and sustainability. We taught machines to think, now we must teach them to forget wisely. 7. Why it impacts our lives. The memory wars aren't just technical. They shape the very fabric of how AI touches our lives. From the apps we use to the policies that govern us, memory constraints influence what models can do, who can build them, and how they behave. Access and inequality. Only a few players, big tech firms and elite labs, can afford the memory infrastructure needed to train frontier models. This creates a knowledge monopoly, where smaller startups, researchers, and developing nations are locked out of innovation. The result? AI tools reflect the priorities of the powerful, not the diverse needs of global communities. When memory becomes currency, intelligence becomes privilege. User experience and limitations. Memory constraints affect how long a chatbot can remember your conversation, how well it summarizes documents, or how accurately it translates. Long context models, like those used for legal, medical, or creative work, are often limited or expensive due to memory costs. This means less personalized, less capable AI for everyday users. Environmental consequences. Every gigabyte of VRAM used in training or inference draws power, generates heat, and requires cooling, often with water-intensive systems. AI-driven services like voice assistants or recommendation engines run millions of times daily, multiplying the energy footprint. As AI adoption grows, so does its carbon and water impact, affecting climate resilience and resource equity. Ethical and cognitive implications. Models trained with memory shortcuts may hallucinate, forget context, or misrepresent facts. In critical domains, healthcare, law, education, this can lead to misinformation, bias, or harm. The memory wars force trade-offs between accuracy, speed, and safety, choices that affect real lives. Surveillance and data retention memory isn't just technical, it's political. The more memory AI systems have, the more they can store, analyze, and retain user data. This raises questions about privacy, consent, and digital rights, especially as models become embedded in daily life. To teach a machine to remember is to teach it to watch, and watching, unchecked, becomes surveillance.